Welcome. Today we're going to learn about the determinant of a matrix. And basically the reason we want to find the determinant is we want to know if a matrix is invertible. And you might ask, well, what does that mean to be invertible? Well, let's first start with an example without matrices, and a simple example of an equation that we need to solve. We have this simple equation here of 3x equaling 21, or 3 times x equaling 21. If I was to ask you to solve this, most of you know to solve this equation, we simply do the inverse operation of multiplication, and we divide both sides by 3. And the 3's are eliminated, and I get x is 7. Well, the problem with matrices is with matrices, you cannot divide. There isn't a division operation, but there is a multiplication operation. So if I relook at this equation of 3x equaling 21, there was another way I could have solved this through multiplication and not division. The way I do that is I multiply by the reciprocal or the inverse or the inverted number of 3. So I multiply by its inverted form, 1/3. And if I multiply the left side of the equation by 1/3, I'm going to multiply the right side of the equation by 1/3. When I multiply by 1/3, I get a number 1. 1/3 times 3 is 1 times x equals, and then 1/3 of 21 is going to be 7. And then 1 times anything is just that number. So x times 1 is just x. So a number times its reciprocal always equals 1. That's true for matrices as well. Matrices, if, by the way, they are invertible, if you multiply a matrix by its inverted matrix, you will get a matrix that's equivalent to 1. In other words, if you have a matrix and you multiply like 2, 3, 5, 6, and you multiply by its inverted matrix, you get out a matrix that's equivalent to 1. By the way, and we'll go into more of this later, but it looks like this, 1, 0, 0, 1. You have these diagonal ones. Today's lesson is not really about this identity matrix at the moment. It's just that if I take now any matrix, any 2x2 matrix, 4, 6, 7, 8, and I multiply by this 1, 0, 0, 1, what I get out is this original matrix, 4, 6, 7, 8. It doesn't change the matrix. And if you want to take the time to do that multiplication, by all means do so. 4 times 1 is 4, 6 times 0 is 0, 4 plus 0 is 4. We get that first term. Then the first row times the second column would give us 6. And then the second row times the first column would give us 7. Second row times the second column would give us 8. So this is called the identity matrix, and we can use that to solve matrices. Again, I'm going to talk a lot more about the identity matrix and actually using it to solve matrix. This lesson, all I want you to be able to do is determine if a matrix is invertible. And we determine that through something's called the determinant. Now, I want to emphasize that not all numbers are invertible. If I said 0 times x equals 21 or 20, you can't invert 0. 1 over 0 is undefined. Like that, there are many matrices that are also undefined when I do an inverse matrix. So, but here's an example, again, of just showing, again, this isn't really the lesson, but I just want to show you. I have some unknown matrix. That's why I have a big X here. It's a 2x2 matrix. I'm multiplying by this matrix, and it equals this matrix. So it's like an unknown times a number equals a number. This matrix here happens to be the inverse or the inverted form of this matrix. So if I multiply that 3, 4, 2, 3 by that, I get this 1, 0, 0, 1. But if I do that to the right side, if I multiply it by this extra matrix on the left, I must also multiply it by the right. So you'll notice this matrix is like that matrix. So when I do multiply these two together, I get this matrix, and any 2 by 2 matrix times this one is just going to be that matrix. When I multiply these two matrices together now, though, I get this matrix. Well, that ends up being our solution then. And so if I took this matrix and plugged it back in to this original matrix up here, so 3, 4, 2, 3, I'm going to do it down here. I'm using this inverted matrix right here, times that, I get that solution of 1, 2, 3, 4. So that was my solution. Now again, I'm just teaching you that what we're trying to do is learn to find this inverted matrix. We don't know what it is initially. We need to figure out what it is. But before I teach you how to figure out what it is, I want to make sure it's possible to find it, because it might not be possible. That's where the determinant comes in. The first thing I want to emphasize is invertible matrices have to be a square matrix. So it has to have the same number of rows as it does column. So a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5. A 2 by 3 you could not invert. So let's talk about how we find if a matrix is invertible. So we're going to talk about finding the determinant. Finding the determinant. Now again, I'm only going to work with you on a 2 by 2. I'm not going to do a 3 by 3 or larger. They get harder and harder. The bigger the matrices, the harder it is to find the determinant. But a 2 by 2 matrix is actually fairly simple to find. To find the determinant, what you do is you take the diagonal numbers 2 and 8 and you multiply them together. 2 times 8. Then you minus off the other two diagonals multiplied together. So I'd minus off 3 times negative 5. The biggest mistake students will make is signs. See this minus sign right here? We just got to make sure we take into account that we're minusing a negative number. So we get 16 plus 15, or 31. The determinant of this matrix is 31. Now, if the determinant is any number but 0, this matrix will have an inverse. Let's see one that comes up with no inverse. This one has no inverse, because if you take these two diagonal numbers, 3 times 4 minus, and then I multiply these two together, 2 times 6, I get 12 minus 12, or 0. If the determinant is 0, the matrix will have no inverse. So, as a formula, as a last rule, because I'm only emphasizing a 2 by 2 matrix, if you have a 2 by 2 matrix, A, B, C, D, A, B, C, D, these are numbers, the determinant is equal to A times D minus B times C, B times C. So again, you're multiplying diagonals, and you do the diagonal from top left to bottom right as the first two, minus the top right to bottom left as the second two. Just write this down, and you should have no difficulty with today's homework, because today's homework is you're just going to calculate the determinant to see if it's a number that's 0 or a number that's not 0, and then say, hey, yeah, this matrix has an inverse. Not that I'm asking you to calculate it yet. Now remember, the number, as long as it's not 0, means it's invertible, and it can be any number. It could end up being negative 486. If it's negative 400, if the determinant is negative 486, it has an inverse. If it's 8,000, it has an inverse. If it's 2, it has an inverse. If it's 7, it has an inverse. If it's negative pi, it has an inverse. I'm not sure how you'd ever get a negative pi, but as long as it's not 0, you have an inverse. If it's 0, you have no inverse. So today's homework should be very simple. If you do have questions, please email me or log on at 1 o'clock, and